Okay, alright. Dengar suara saya? Can you guys hear me? Okay. So this just to review, there are some advantage and disadvantages of direct online for reverse. Advantage dia, direct online ni dia is most economical, the cheapest motor, is simple to establish, to operate and maintain. Circuit dia pun simple. You tengok circuit dia during the first part A, part B kan. You just only use one contactor. Okay, or two contactors. Dia provide 100% talk the time and only one set of cable required lah. But disadvantage dia, direct online ni require, it will allow motor to operate at a very high starting current. It can be up to 6 to 8 times. Kalau if the normal operating current is 1 ampere, then it can start during starting it can go up to 6 or 7 or 8 ampere lah. So this starting high current ni can cause thermal damage or thermal stress on the motor. Thereby dia akan reduce dia punya life lah. So and then starting current link can also cause large voltage drop in electrical installation. So basically the direct online is not suitable for large motor. Okay, more than 5 kilowatt, 10 kilowatt, 100 kilowatt. So it's not suitable. So for example, large water pump, large compressor. Okay. So in other words, the direct online or for reverse is only suitable for small motor, less than 5 kilowatt. Okay, because the higher the power of the motor, the higher the starting current. The higher the starting current, the higher the impact or the higher the impact that you will have to the winding as well as the system. So okay, this is what I just said just now. So as an alternative, engineers have designed what they call a star delta or delta motor starter to reduce the starting or inrush current. Okay, so as I said before, okay, generally you can read this through, but basically what the star delta motor starter do is that it will basically configure the circuit in such a way that during starting the motor will be connected in star initially. Okay, and then after a few moments it will switch over to delta connection. So basically this motor can be configured in two connections. Okay, so after that it will keep running on delta until the motor stops. Right. Okay, this is to show you some overview or some picture how the winding looks like. So because basically star delta is basically you are configuring the winding connection of the motor, not the rotating part but the stator part, the static part. This one is the static part. The rotating part is in the middle here, which is already now you can see this figure is already removed. Okay, so the outside here, this winding that you see here basically is the stator winding. Stator winding is come from the static winding lah, means the winding does not move. So the stator winding basically to provide the electric or magnetic field in order to move the rotating motor in the middle. So if you see the cutoff view of the motor, you will see that there are basically three windings. Basically, this is a red, green, and blue, or red, yellow, blue, because three phase. Because we have the red, yellow, and blue phase, so we have three windings, three set of windings. And each winding have basically two terminals, starting terminal and the end terminal. Okay, sorry about that. So since we have three phase, then we have 1, 2, 3, 4, 5, 6 terminals lah. Okay, so this 6 terminal basically what you are going to configure, you're going to connect in such a way that it can be configured as a star or delta. We'll talk about star delta after this. And I hope you have watched the video that I sent you in Telegram. Those are very basic introduction on how star delta system works. Okay, this is a motor. This is U10 motor. This is also in U10. Okay, this is the Lorenzo motor. It's in the power system lab. All right. So there are few junction or terminal box. Okay. Terminal box that basically here are basically the winding is in this motor here, all winding here. Okay. But and then in the end it will all the terminal will end up in this box. For example, this is one set of terminal, this is two set of terminal for phase B and another set for phase C, for example. So 6 terminals are all inside this box. Same here lah, up here. As you can see that there are not really 6, but there are also some terminal for neutral and also others lah. Okay. Okay, so 6 terminal. So how are you going to configure this 6 terminal? Okay, sorry about that. One moment. Oops. So basically, you will have, this is a junction box. This is the junction box here. And basically it's configured this way. So L1, L2 and L3 are the main power supply. So this one here is the main power supply. You have the power lead from the red, yellow, blue. Okay, this is red, the yellow, blue power supply incoming in there. And then you have a level. Okay, in a European type of motor, the winding are level in terms of letter U, V, and W. Okay. So U1, V1 and W are 1, which is here. U1, V1 and W1 are basically the three phase winding of the incoming or the start lah. Incoming is a static. Start the beginning, terminal of the winding. Okay, so this is a terminal winding and you will connect. This is part of the wire winding. Okay, and you have a winding. This is basically the winding. Okay, and then the winding will end at terminal U2. Okay, so U1 is the beginning, U basically U winding, V winding, and W winding. Okay, for U you have U1 is the beginning and U2 is the ending. So the wire here that I show you in red here basically is not shown. Basically is inside the motor. Okay, the wire here that I'm showing here is inside the motor. You cannot see it's outside. All right, this is just to show you that the terminal here is connected to the winding, and then the other end of the winding is connected to terminal U2. Faham eh? Okay, so let us, all right. So, and then, okay, as I said before, U2, the V2 and W2 are the three phase of the outgoing or the other side of the winding. So basically this is one side of the winding. For example, this is W2 and the other side is W1 here, okay. So I hope you understand that this is just a schematic drawing that to show you that how it's connected. This is crisscross, it's not really straight. Okay, so in between 1 and 2 are the windings. For example, for U winding, disconnected between U1 and U2. You can read this all on your own. I just explained it just now. Okay, faham eh? Any question on the macam mana the terminal box is configured? Okay, and dia punya arrangement, the arrangement is just the way that this is U1, V1, W1, W2, U2, and V2. Okay, why didn't put U2, U1, and U2 here? I'm not sure, but basically it's easier to show in the drawing lah, the connection here. Okay, all right, so let us talk about what is star or Y and delta connection. Okay, star, first kali star. So basically it is a type of connection where one of the terminal of each of the three winding are connected to a common point. Okay, let's say these are all the three windings, winding red, yellow, and blue, right? This is the winding of the motor, the winding of the motor. So at one end you short them together and connect them to a neutral point. Okay, at the other three ends you will connect them to the phase red, yellow, or blue of the power supply. Okay, so if you draw like this, you can also draw the diagram like this. So that's why it's called star or Y, because if you draw it like this, it will look like a letter Y, like a upside Y or star, right? Okay, so that's why it's called star or Y configuration. Okay, just talk about the configuration only, how it is connected only. Configuration means how the winding is connected. So one end is shorted together into a neutral point, and the other one is connected individually to the power supply. Okay, all right, I just mentioned it now. So what is delta configuration? A delta configuration is the type of connection where the three windings are connected in such a way that it forms a closed loop. Okay, let's say the same, the winding are all the same. Okay, let's say these two windings are on the top here and the bottom here are from the same motor. Okay, the same kilowatt, the same horsepower, and basically each winding has the same resistance and inductance. Okay, but if you connect them in such a way that, okay, for red phase A, the first terminal connect to the end terminal of the second phase, and then the first terminal of the second phase connect to the second terminal of the third phase, and the first phase of the third terminal will connect to the last terminal of the first phase. Okay, as you can see, it perform like a loop. Okay, it connect everything like a loop, or maybe something like a circle, right? So there's no wire pointing out, only a complete loop, like a area lah. So if you redraw again, you can redraw this circuit into a triangle, okay, or a delta, okay. In Roman symbol, it's called a delta. You see this is what I call a delta configuration, like a triangle here, okay. So, and then, okay, after you connect them into a closed loop, and then the other junction, all the junction, the interconnection junction here and here is connected to all the three phase of the power supply. Okay, so that's how you configure or you wire up, you connect the same three winding, red, yellow, blue, into star or delta. Okay, do you guys paham? Any question? Okay, if there's any question, kita akan proceed. Okay. So this is in practice lah. So how to configure connection star or Y connection in motor starting. Okay, so as I mentioned just now, I think this is just another more detailed explanation, but actually it's very simple. Okay, if you in actual lah, basically in some type of motor, basically you short circuit or connect together the terminal W2, U2, and V2. So basically this is a terminal here, W2, U2, and V2. You short them together. Okay. So this basically just you see that this round thing here is basically what you call a jumper link. It's like a piece of metal. You just short them between the two terminal. Okay. And then you have another jumper link here to short between U2 and V2. This is similar to this kind of connection here. This is a more simplified diagram to show you you connect the other end of the W, U, and V winding together. Okay, and then in the end, this will connect to neutral point. Okay, it is not shown here lah, but actually this will connect in the end to the neutral point. All right. Okay, and then after that, you connect the power supply to any point of W1, U1, and V1. So, and then this U1, V1, and W1, you connected to L1, L2, and L3. Okay, red, yellow, blue. Okay, so this is diagram just to show you the another similar diagram. So basically, this is look like a Y diagram, but just showing you the terminal connection lah. Okay, the terminal connection. Yeah. So you see there's U2, V2, and M2 is jump together or connect shorted together. Okay. Also this one. So these three different diagram, but actually it shows the same thing. This one, this diagram only will show you just with the winding collection lah. But this winding basically is hidden lah. You cannot see it physically from outside. Okay. So similarly, with then having said that, for delta configuration, to do that basically is even simpler. All you have to do is you connect W2 to U1, U2 to V2, and V1 to V1. Basically, W2 to U1, you connect them together. U2 to V1, you connect them together. V2 to W1, you connect them together. Okay. So if you connect them together, you can see that this will form like a loop. See, if I trace the line here, right? I trace the line here, we connect here, and here, and here, connect here, and here, and here. Nampak? You will see like a loop, betul? Alright? You will go back to the original point here. Okay? So a simplified way, this is without the winding, but if you can see this one and this one's pretty much similar lah. Okay? Alright. Okay, let's talk about voltage in star delta configuration. This is very important. Okay, there are two types of voltage in motor. Firstly, is the type of voltage is called a line voltage. A line voltage, if you have seen the video that I shared with you, basically it's a fixed supply voltage between the phase for each supply. This is between the phase. If you take, for example, red and yellow, you measure the voltage between phase red and yellow, you will have what is called the line voltage. Okay, let's say this is a three-phase wire coming out. You feel wire coming, just apply. If you have a multimeter, a voltmeter, if you measure the voltage between these two phases, you will have what you call a line voltage. If you measure between these two phases, you will have also the line voltage. And if you measure between these two phases, you will have also the line voltage. And these three line voltage has the same value, but it will have this different phase. Okay, different angle and magnitude is the same, but the angle is different. Okay. All right, in Malaysia, the voltage, okay, I forgot to finish this one. Basically, for a line voltage in Malaysia is around 415 volt. Okay, this is, you can also sometimes call it voltage phase to phase. This is a symbol for phase. All right, 415 volt for low voltage network. Okay, for high voltage, it might be higher, maybe 33 kV and stuff like that. And then there's another type of voltage, is the first type voltage. Another type voltage is called a phase voltage. Basically, the phase voltage is the voltage across the motor winding. The value of the phase voltage depends on either the winding is configured as star or delta. Okay. All right. Line voltage is normally fixed voltage, but the phase voltage or the voltage across the winding will be different depending on how you connect the winding. Okay, I'll show you after this. And then another thing that you have to remember is that the current from the power supply vary. Means that it will depend on the impedance or resistance of the motor winding. Okay, if the impedance go up, the current go down, and vice versa. So remember Ohm's law, I equals P over R, right? So if you have a higher resistance, then if your resistance go up and your current will go down, okay, and vice versa. Okay. This is a snapshot of the video that I showed you before. So you have the phase voltage across all the three winding. This is the three winding of the motor. Okay, this is the line voltage across between, let's say for example, this one is between red and yellow, and the rest of the other line voltage. Okay, so what is the relationship between the line voltage and phase voltage? Okay. All right, to simplify for the sake of this lab, we are not going to discuss about the theoretical calculation, how we derive the relationship. But I think it's, for now, it's enough for you to remember that the line voltage only for star configuration is square root of 3 multiplied by the phase voltage of the star connection. Okay. All right. So in the end, the phase voltage, if you connected for, the voltage across each winding for star connection will be the fixed line voltage divided by SERT3, which is around 1.732 something. Okay, so meaning that the phase voltage will be less than the line voltage, right? Okay, because the line voltage is reduced, so the phase voltage will receive less voltage. For example, if the line voltage is to let's say 415, so the phase voltage will be 415 divided by 1.732, which is what? 415 divided by 1.732. You have around 240 volt. Okay, this is what they call the phase voltage. This is what the voltage for each winding will experience. Okay, how about delta? Okay, delta. See, this is the same winding. Let's say this the same winding has the same resistance. This is also same resistance, R1 and R1 value, and R2 all the same value resistance. If you disconnect the star winding and reconnect again the motor into this configuration, okay, all right, basically what we have is that the phase voltage, so the line voltage, sorry, will be equal to the phase voltage, because you see these two are measured from the same point, right? Okay, so the line voltage and the phase voltage will be equal. So basically you are applying higher voltage into each phase of the motor compared to star configuration. Faham tak? Okay, so enough for you to know right now that the delta configuration, basically the line voltage will be equal to the phase voltage. Basically the voltage of each phase will be higher lah. So if we fix the line voltage, the voltage phase voltage of the star connection is less than phase voltage of the delta. Okay, so in the end, if you have less voltage, you will eventually have less current and lend the delta current. Okay, all right. So that is, I think, so for now you need to remember only that part lah. Okay. Okay. This one thing that I think you remember we didn't use in our first part, okay? It's called a timer. Okay, I think I've explained this before. What is a timer? It's basically it's a device. It looks like this. Okay, there is a number like a speedometer in your car, but it's not a speedometer. This is basically the time. 1 second, 2 seconds, 3 seconds, and this is the indication from changing from Wye connection to delta connection. Okay, and this is a sequence delay adjustment, and this is a timer adjustment. And you can change the timer scale by just pushing this knob left or right. Okay, basically you can change the timer here according to your desired value lah. Okay, 5 seconds or 6 seconds, maximum 6 seconds lah. Okay, so this is a type of tool used to control. It's like a clock. It's like an alarm clock. A timer basically like an alarm clock. It will activate, turn on, okay, when the time comes to its setting. Okay, so these are all the terminal connection. If you can zoom in this one, basically, okay, these are all the terminal connection here. Okay, so how you can connect them in physically, because timer also have a coil. Okay, it has to has a supply coil which is connected to terminal 2 and 7. Okay, physically in this equipment, and you have also a normally open point switch, and you have a Wye connection switch and delta connection switch. Okay, so the most important thing is this. Okay, how it operates when the current flow to the coil. Okay, when you start to switch on the current flow to the coil, the timer will start to count. Let's say you set 6 seconds. So we start 0, 0.1, 2, 3, 4, 5, 6. Okay, let's say when it reaches the set value, when it reaches, let's say you set 6 seconds, all the switches will change status. Switches inside here, normally open switch, Wye data switch, or for example, if it's normally open, will close, and normally closed switch will open. Okay, enough. It's easy to say that when the timer reach its setting, it will operate, change all the status of the switch in the circuit. Okay, now let's talk about one of the most important part, which is how the circuit start data works. Okay, this is very important, and I hope you please pay attention to this one, because I'm gonna say this only once. Also, although you can repeat the video lah later on kan. But anyway, let's make sure it's recorded. Okay, recorded. All right, so. Okay, I think I'll go to not to whiteboard. I go to whiteboard. Let's go by my whiteboard. Okay, it's easier to draw in this part using this software. Okay, so you have this the circuit is the same. I mean, almost the same. You have it's divided into two type, which is main circuit. So main circuit and control circuit. Okay. So the main circuit, as you can see, you have all the 3-phase supply, 415 volt. Remember, 415 is between, let's say, red to yellow, or yellow to blue, or blue to red. Okay, so the 3-phase, the line voltage. So V15 basically is the line voltage. Okay. So and then you have all these phase connected to a MCB as usual. I think it's the same equipment before. And all connected to, okay, there is also a connection here, connection here, connection here, connection here. Okay, go to the contactor C1, and then go to overload switch as usual, and in the end you will have the motor. Okay, and then if you can see, the motor here have 6 terminal, 1, 2, 3 on the top, and 1, 2, 3 at the bottom. Okay, nampak tak? So before this, kalau you tengok direct online, you only have 1, 2, 3 and the neutral on the earth cable only. But now you have 6 terminal. Okay. Okay, let me try to change dia punya size dia. Macam mana tukar size dia? Okay, besar sikit. Besar sikit. Okay. Alright. So another thing, if you observe in this star data circuit, you have 3 contactors, C1, C2, C3, and C2. Okay. Alright. So C1, C2, and C3. So the way it is connected, okay, I will explain to you after this. Alright. So let's talk about the control circuit. Okay. So in your MATLAB, you have to configure the circuit to basically to replicate this circuit. Okay. All right. So let's move it a little bit smaller. Okay. So this is a control circuit. So okay, let me draw it in red. Okay. So you have an overload switch here. You have a stop button. Remember, stop and start button here are temporary. Remember, it's a temporary means that if you push a start button, it will bounce back to open position. Okay, it's like a spring. Remember, I briefed you before, kan? Okay, so let's discuss about when you start the network. Okay, okay, we will go along to look at how this circuit operate one step at a time. Okay. Now, if once you push the start button, downward, okay, the contact here will close. Okay. Once you have the contact closed, the current, okay, is taken from one of the blue phase here. The current will start to flow in through the MCB, okay, and through this connection here, this is connection, and through the overload switch, because it's normally closed, through the stop button because it's normally closed, and then through here, and then it will split into two. Okay, one go to the contactor coil, and another one will go to the timer. Okay, timer circuit. Okay, and then it will return back to neutral lah. Of course, you have to have a return path to back to neutral. Okay, all the way down there. Okay. All right. So what happens that once you energize this coil, at the same time, sorry, it will also go down here, and it will energize the run light, which is the light will turn on. Okay. So all these three elements will be energized: the run light, the timer, as well as the coil. This is a coil, coil for the main contactor. We call it main contactor lah, C1 main contactor. Okay, once the C1 contactor coil is energized, all the C1 contactor will change status. Okay, look, okay, you have a C1. Oh, sorry. Okay, before that, okay, let's take a look here. Okay, this is C1 over here. So C1 here will also close. This one also close. This one is also close. Okay, all right. And then at the same time, the C1 contactor will also close here because this coil here also activate this C1 switch here. So the current can also flow from this way. Okay. So, and then after that, you remember that once we push the start button, you will have to remove your finger, and then this start button will go back to open, right? So what will happen is that this start button will disconnect. Okay, so the current will not flow through the start button anymore, but instead it will flow through the C1 contact here and all the other three branches. Nampak tak? So the C1, the coil, the timer, and this run light will still be energized, although the start button has gone back to his normal position, which is normally open, because it's a spring. Remember, there's a spring down here, right? You push once, and then you release your finger, and then we'll go back to open. Okay, so the current will keep flowing this way. Sorry. Okay, so and then after that, what happened? Okay, that as I remember, as I told before, okay, the timer here, the coil is energized, but again, and then the timer will start to count 1 second, 2 seconds, 3, until it reaches the setting. For example, let's say we set it to 6 seconds. Let's say 6 seconds. Okay, let's take a look at other part if I forgot. Okay, so after 6 seconds, okay, okay, before 6 seconds, let's say for between 0 and 5 seconds, nothing will happen to the timer switch, which is this one, T and T here down here, right? You see there's T here. This is a normally closed timer switch. This is a normally open timer switch. Okay, so nothing will happen between 0 to 5, but once the time reaches 6 seconds, okay, this timer will open. Sorry. Basically, the timer here will activate, and this T, okay. Before I forgot about that, I think I forgot to mention that. Okay, at the same time, okay, during the overload energization of C1, T, and timer here, the current will also flow to this branch through the timer contact normally open to C3 and to C2. Okay, star contactor. So C2 will energize. Okay, once C2 energize, okay, this C2 over here will also close. Okay, and at the same time, if you look at here, the C2 here will open. Okay, so C2 here will open. So you see that this, and then the run light will light, the timer will count, and the main contactor is still there. And you can see that the star contactor will operate. So the C2 here basically operates as a star contactor. You can see that, okay, this is C. Remember that the star contactor, you have all the winding connected together, kan? If you try to trace the line, so this is the winding, for example, go from here, the red one, go from here to this point, and then to this one, and then all the other three also lah. See, the other end of the winding is shorted out. Okay, this is go to neutral, right? So this is similar to what you call, because this one is open, C3 is still open, right? So the current will not flow to the other way around. So it will go from here to here, right? And then to C2. So the winding of the motor is connected in such a way that it will look like a star connection. Okay, so C2 will cause the connection of the C2 will cause the motor to operate in star configuration. Okay, paham eh? Okay, next what happened? Okay, the timer starts 0, 1, 2, 3 until 6. Now, when the timer reach 6 seconds, what will happen? Okay, when the timer, as I said before, when timers reach the setting of the time, okay, this timer will operate. So all the switches will switch over. Okay, okay, let's take a look. Where are the timer switches? Okay, so this is 1T here and 1T here, right? So this timer is normally closed, but what happen? It will go to normally open. Okay, so if I draw here, so now this switch here will open. So there's no current going through this path anymore, and this switch here, the T down here will close. So then, okay, all right. Sorry, C2 here is normally closed. Okay, and then after that, the current, okay, C1, this will energize here. The current will flow through T and C3, and it will energize C2. Okay, remember, C2 is energized. Once it's energized, it will close back this C2. Okay. So sorry about that. I forgot. Sorry, my mistake. Let me replace that again. So this timer is disconnected. There's no more current flowing to T1 here because this timer is open, and there's no current. This is open, and then this one is closed. So the current will flow through this timer and flow through C2, and it will energize C3. Okay. So C2 will de-energize. So once C2 dis-energized, there's no current flowing the coil of C2. So there will be no this contactor C2 will go back to original position, which is open, right? So and then this C2 here will also go to original position, which is closed, right? Okay. So let me erase this one. Okay. So this will close, and then the C3 contactor will energize, and then once the C3 energized, this C3 also will close. 1, 2, 3. Now before it's normally open. If it's energized, then it will become closed. Okay. All right. So once the C3 is closed, then if you want to trace the line, then it will act like a delta. It will cause the network to configure. For example, this terminal, red terminal, connected here and connected to the front here, right? And then yellow connected to the front here, and the blue connected to the front here. As you can see that it formed like a closed loop, a delta connection. All right. So this is C3 is the delta contactor. Okay. And then at the same time, okay, now the time is running some until 6, right? And then C3, okay, at the same time, this switch will also close. Okay, so you have two paths running, the current going from here to here. Okay, all right. So and then after the timer finish, okay, let's say during delta, let's say maybe there's something happen whatsoever. All right, if someone operate the timer automatically, for example, if you open this switch here, let's say somebody open this timer switch here, and it will not interrupt the current because the current can still flow to the C3 through to the C3 coil through to here. Okay, it will hold the contact for C3 until the motor stops. Okay, all right. So the motor will operate in data connection until you manually stop the operation of the motor. You open this switch here, you push the stop button, and the entire circuit will disconnect. And then and after that, it will go back to original. Okay, all the switch here will open, C1 open, C3 open, everything goes back to original. Okay, so that basically how the star data works. And there's also if you see here down here is an overload trip switch. If the current let's say sense see basically there's a sensor here connected to the wire here. If it sense a high current, and it will automatically switch on, and then if it switch on, it will bypass this overload switch, will close, this overload switch will open. Okay, and all the current will flow through this point down here, okay, to the trip light and bypass all the contactor. Okay, so basically if you have an overload, all there's no more current flowing through all this part of the circuit anymore. It will go straight to the trip light. Okay, it's no more. Okay, so then goes to the trip light will light up, and then we go straight to the neutral. Okay, so the contactor C1, the timer, everything will cease to operate, and then basically you have an overload trip situation. Okay, so I hope you understand. Any question? Berita, you guys understand how this thing operates? I can see that Aiman is already inside. Yeah, I think we have a full class today. All right. Okay, so let's move on to the. I think let me see if there's more thing in the slide. Let me check. Okay, there's one more thing I want to explain before we move on to MATLAB. Okay, so there is this calculation. Okay, so one of the things that you might want to know is that basically you have this thermal overload relay setting, right? So the thermal overload relay has some setting. You can set a certain current level, maybe 1 time or 2 times the normal current. So, but the problem is how are you going to know how to set the relay setting, how to calculate the relay setting. So let's take a look at one example, and I'll show you how. Okay, so let's take a look at this example. You have a 30 horsepower induction motor. Okay, so assume the motor operate at a power factor of 0.85. If you have learned about electrical system about power factor, then I think it's okay. But for those who have not, if you don't know what power factor is, you can go ahead and maybe look for other references, or maybe just assume now there's a power factor. Each motor has a certain power factor, 0.8, normally 0.9, maybe 0.7 is very low. Okay, so power factor is a fixed number for each motor. Okay, and then there's another factor number, basically is what you call a safety factor. Okay, let's say we said it's 1.2. Okay, what does it mean? A safety factor of 1.2, for example, it means that the thermal overload will operate when the current goes beyond 1.2 times. Times maksudnya multiply lah, times the normal current. Let's say normal current is 10 ampere. If it goes beyond, let's say 12 ampere, then the overload will operate. Okay, understand? All right. So let's take a look. Let's how to find the setting for the thermal overload relay. So first you have to convert the horsepower into watt. Okay, 1 horsepower equal to 746 watt or 0.746 kilowatt. So 30 horsepower equals to around 22.38 kilowatt. Okay, so as you can see, this is quite a large motor. Okay, more than 5 kilowatt. So okay, so step 2. Okay, this formula, you need to calculate the normal operating current of the motor using this basic formula. Okay, for any type of equipment, I think not necessarily motor, you can calculate the, normally motor lah because of power factor, calculate the power in terms of watt equals to square root of 3 multiplied by the line current multiplied by the line voltage multiplied by the power factor. Okay. And I think I forgot to mention that the voltage here, I think the question here, the line voltage is 415 volt. Okay, please note that down. Okay, I will share you this slide later on in Microsoft Teams. All right, so you can take a look again at this slide. Okay, just correct, just add this one here. The line voltage is applied is 415 volt. Okay, so where P is the power in watt, L is the line current, VR is the voltage, and P is the power factor. Power factor basically is the constant value of the motor. Okay, each motor may have a different power factor value. So if you arrange this formula, you can calculate the line current. Basically, this line current is the current that flow to the winding of the motor. So it's P divided by all this. If you just rearrange, right? So you pick and then you put on all the value that we have calculated before. This is the power. This is the voltage line is 415 and 0.85 is the power factor. And you will have the current value is around 3615 amp. It's a very, very large current. Okay, you don't want to play with this current. It's very dangerous. Okay, so and then step number 3, the last step, you multiply the safety factor to the normal operating current to get the thermal overload current setting. Okay, let's say you calculate that the normal current is 36.58 multiplied by 1.2 and the thermal overload relay setting is 43.9 amp. What does it mean? Meaning that if the current goes below 1.2, below 43.9, let's say maybe it goes up to 40, maybe 41, the thermal overload relay will not operate. But once the current reach 43.9 and above, then the thermal overload relay will operate and will stop the operation of the motor instantaneously. Okay, so that's how you set. Okay, this is how the basic formula. Maybe this will go into the quiz or something like that. Okay, so you make sure you understand how this thermal overload relay is calculated. Okay, let's move on to last part. Okay, to your MATLAB. Okay. So let's switch over to MATLAB now. Okay, do you guys see this? Boleh? Okay, so this is the file of the MATLAB. Okay, I'm aware that maybe some of you, I hope you have done part A and part B. If not all, maybe some. Okay, so make sure you have you know how to connect certain basic things, because in this part, certain connection are also is quite similar. Okay, for example, if you look here, the 3-phase supply circuit here. Okay, here I also use the same main circuit, right? In the main power supply, the same line here. Except, sorry, in this part you will have oops, sorry. What did I do? Okay. All right, you have some extra contactor. You will have basically contactor C3, you have contactor, I think, C2, and you have a contactor C1. You have 3 different contactor. Okay, and then the rest are all the same. I think you have it's a voltage source, the same voltage source, the same MCB, and the same stop button and start button as before. All right, and another new thing in this circuit is you have a timer circuit here. Okay, a timer circuit. Where's the timer circuit? So for timer circuit, so you have a coil. CO means coil. This is the input and output. Positive is going in, negative is going out. Okay, normally this is a normally open. This is normally open input and out. Okay, normally close and normally close input and out. So if you look here, see how to relate that. For example, I share with you lah. This is a normally closed timer switch, which means that this is the connection here lah. Normally closed switch here. Okay, where it comes the input here, and C plus is basically this point here. Okay, this point here, and C plus is point here, and C minus is this point here. Okay, so your task is to trace all the connection lah. Okay, so if for example, if you want to connect between this point to this point here, okay, make sure you trace that. You tick, okay, I can make this one, you tick, okay, this one also tick, okay. So you need to connect them one by one, and you have to follow the circuit, the schematic of the circuit, okay. All right, so the rest of the thing are the same. Okay, this have your thermal overload relay, okay, the contactor. Make sure you refer to this schematic every time you make the connection. Okay, once we make the connection over the component on your left side, you put a tick mark here. Okay, I've done this, I've done that. Okay, and then after that you can run the simulation. Okay. All right, so let me show you. Okay, the operation, how to operate this starletta is very simple. It's almost similar with the first part A. You basically just start, stop, and on button. Okay, so let me go here. Okay, in this circuit, I have modified, not modified, but basically just to show you that the on button here for both stop and start button refer to close, and the off button refer to open. For those who cannot remember this, what I did is that I double click this one, will open up this window, and I just change the word here, down here. I put add equal to close, off equal to open. You can type here as you wish lah, for example, kan. Okay. Okay, and then you can apply, and you will change the symbol of this switch here. Okay, so make sure before you start, you have to make sure that all the switch and on off position, start and stop button is equal to initial. It says stop is close, start is open. So when stop, close, start, open. So stop is close. Close means up here. Here means open. Here means close. It's a what you call toggle switch, like a seesaw switch. So if it's up here, it's closed. Down here is open. So it's closed, and then the start button here is open. Sorry, open here. Okay. So this is your initial part. Okay, assuming that you have done all the wiring lah. Okay, you have finished all the wiring, you connect everywhere, and then after that you can push the run button. Okay, the timer is set at 0.8 second here. Okay, as you can see, 0.8 second. So you can change that if you want to, but I think 0.8 is actually quite long. It's enough. You have enough time to complete the simulation. You just have to click start button once and then start button twice. Okay, so you click once, wait for a few seconds, and then after that you stop again. So this is to stimulate you push and then you release the start button. So just because we don't have the type of release function, so you have to manually manually close and manually open back. Okay. Okay, so let's take a look how. Okay, again, in the end here, you also have the scope to show you the result. Okay, if I double click, it will show nothing lah, basically, because it's not run. The simulation has not run yet. Okay, let me demonstrate to you how the result would look like. Okay, so let me close this one and I open up the instructor version. Okay, this is the instructor version. Okay, I darken all the background because all the connection are there. Okay, so how do we run? Okay, let's make sure that you have the timer ready and all connections are made. Okay, now let's run the simulation. Okay. Okay, one moment. Let me have to prepare like this. Okay, one moment. Okay, so this is normally the stop. Initially, you have to close the stop button and open the start button. Okay, so let me click run. Okay, once you click run, you have to wait. You know, to wait for a few moments. See down here, you can see it's compiling, right? It's compiling and depends on your computer speed. Okay, once it's finished compiling and you see the timer here start, right? 0.03%, 6%, and you can operate. Okay, now I push close one time. See, the status now changed to 1. And then I push close one more time, so the status goes to 0. And then that's it. I just wait until the simulation finish. Okay, so now what you have to do, you don't have to do anything. You just wait until the simulation ends. Okay, 67%, 68% down here. If you look, down here is almost finished. 76, 86, 88, 90%. Okay, almost done. Okay, now you're done. Okay, what you need to do now is basically you go to your answer here to your scope. Okay, this is your scope. Double click the scope. Wait for a while. Okay, it might take a while. Okay, so this is the result. All right, so if you look, okay, the result are divided into 3 set of graphs. So the first graph here basically shows you the stator current or the motor current. Okay, so the yellow is the A, blue is B, what you got, orange is C. So it's the 3 phase, all the 3 phases, red, yellow, and blue lah. Okay, so okay, and then the second graph here shows the voltage measurement. Okay, the voltage measurement is basically voltage measurement 1 and 2. Okay, so basically this is all the voltage of the 3 phase of the motor. All right, and then the last part here is the status of the on-off switch, whether it's on star or delta. All right, so okay, let's take a look. Okay, take a look at the bottom graph here. So at from time 0 to, let's say this is 0.05. Okay, there's nothing happen here. And then I suddenly push the start switch. Okay, start switch, and then the delta, the star switch will turn on, goes to from status 0 to status 1. Okay, and then after that I'll just push the stop button, and then I just off again. Okay, off again. All right, so when I off again, okay, during the start here, you see that the current here will the voltage, let's talk about the current here, will increase. Okay, but it will increase in a much less current. Maybe this is around 20 ampere. Okay, 20 ampere during starting. See, and then it will this is what you call the inrush current. Okay, remember that in the first stage here, the motor is running in star. Okay, and the voltage here also, the voltage, the phase voltage is square root of 3 less than the line voltage. Okay, all right. So after a few seconds, this is a timer circuit. For example, from this time here to this time here is where the timer start to count from 0, 1, 2, 3, 4 until it reach at this time. Okay, the timer will switch over. See, this is basically the yellow line below here is not the start button, push start button. This is basically the timer circuit, the timer switch. Okay, so the timer switch will change over from star. See, the star will go to status 0 and the delta will go to status 1. Okay, so what will happen is that it will remember the circuit that I have shown you before. It will change over from star contactor to delta contactor. Okay, this is what happened at this moment. Okay, so what happened is that the voltage will change over from star voltage. This is a star voltage here is less, right? This is this is the current. Sorry, let's talk about the voltage first. The current, the voltage here is like 240 volt, right? Okay, so but once you have switch over to delta, the voltage will go up to 415 volt. See, you can see this is a 600 volt here is the peak current, right? The peak voltage. So the peak voltage is 600 volt, but the RMS voltage, which is the line voltage, is 415 voltage. So 415 volt. So you see, it has increased. The stator, the motor voltage across the winding has increased from let's say this is 240 RMS to 415 RMS. Or you can say this is from, let's say this is value around 300 peak to 600 peak value. All right, so basically you can see it's an increase lah. Okay, and the current also has increased. This is a normal operating current here, and this is the normal operating current for the delta connection. See, because the motor can operate at less current, but it will not be very effective, right? If you operate that at low voltage, then the motor will spin quite slowly. And then after that, when you switch to delta, you will, once it receives a higher voltage, and then the motor will start to spin up very quickly up to its rated value. Okay, it's like I share you the video of the motor starting, right? Remember the first, when you start the motor in star, the sound is very slow, right? Once, and then after that, the motor has start gaining momentum, and then we switch over to delta, and when the motor starts spinning very fast, go up to its rated speed. Rated speed means that the normal speed lah. Initially in star, the speed is very less. Okay, because imagine like you have you're driving a car lah kan. You cannot simply go straight to 100 kilometer per hour, right? You have to go slow, and then suddenly you increase the fuel, your motor will go faster, right? Okay, similar to like a motor here, it has to gain some momentum because motor stator is very heavy. You cannot simply push to a very high RPM or high velocity initially. Yes, you have to go too slowly. If you push too much voltage or current initially, then that's why you have a high inrush current. Okay, if you refer to your part A, part A before, part B, you can see that the inrush current here in star delta is much less than the one that you have right now. Okay, much higher. Sorry, the previously part A, part B, you can see the inrush current is very high compared to this one. Okay, so this is the result that you should get, and this is what you should be able to explain in your video. Okay. So I think that's about it for my discussion today. Let's go back to the slide. I think there's no more. Okay. Do you have any question? Okay. It's almost 1 hour now, 1 hour plus. So I think you can go ahead and wire up the star delta if you haven't not started yet. But if you have started it, please continue to prepare your video, okay? Your slides and also your, yeah. Okay, so any question? Okay, let me stop recording the video now, okay?